We've discussed sequences and what they are, and we've discussed the inductive axiom. And now what we're going to do is we're going to do inductive proofs regarding sequences. So in an earlier video, we saw the sequence where a sub 0 is 3 and an plus 1 is an plus 2. This was a recursively defined sequence. Could also be called a one-step recursive sequence because to get a single term of the sequence, you need one term before it. So we computed several terms of the sequence, and they were 3, that's a sub 0, a1 was 5, a2 was 7, and then 9, and so forth. Now it certainly looks as if the terms of this sequence can be computed by an explicit formula, where a sub n is 2 times n plus 3. Now you can check that if n is 0, you get a sub 0 equals 3, which was correct. For n equals 1, you'll get a sub 1 equals 2 plus 3 or 5, which does match what we computed based on the recursive definition, and so forth. Does this formula, however, always hold? In other words, we're asking, is the following statement true? Given any natural number, a sub n equals 2n plus 3. We don't actually know that this is true yet because what we were given was this recursive formula, but now we have formulated a statement and we're going to try to verify that it's true. Since this is a statement that applies to all natural numbers, for all n, a sub n equals 2n plus 3, the main tool for doing that proof will be a proof by induction. We want to show that the truth statement for this, a sub n equals 2n plus 3, is in fact all natural numbers. So what we want to do is to show first the statement is true for n equals 0, that a sub 0 really is 2 times 0 plus 3. Then what we're going to do is if I assume the statement is true for a certain n, that a sub n really is 2n plus 3, then does the statement hold for n plus 1? Is a sub n plus 1 equal to 2 times n plus 1 plus 3? In other words, we're going to do a proof by induction. Having formulated the statement a sub n equals 2n plus 3, if we can show that it's true for 0, and whenever it's true for a given n, it must be true for n plus 1, we will have shown using the inductive axiom that the truth set for our statement is all natural numbers. In other words, it is always true. So we have to check two separate things. Is it true that a sub 0 is 2 times 0 plus 3? Recall that this is called the base case of an inductive proof. And furthermore, if we assume it is true for a certain n, can we then derive that it must be true for the next one? And this was the inductive step. And recall that the assumption that a sub n is 2n plus 3 is called the inductive hypothesis. Well then, let's charge ahead and try an example. Suppose that we have a sequence where a sub 0 is 3 and a sub n plus 1 is equal to an plus 2 for any natural number n. Prove that for any natural number n, we must have a sub n is 2n plus 3. In other words, let's go ahead and prove the assertion we made on the previous slide. Well, let's begin the proof. We start by establishing the base case. Is our claim true if we specifically choose n equals 0, the first natural number? In other words, we're trying to verify that our assertion right here, a sub 0 equals 2 times 0 plus 3. Well, we were given that a sub 0 equals 3, which does match 2 times 0 plus 3. So in other words, if n is 0, our claim is true. Then we do the inductive step. If we assume this claim is true for some n, does that then imply that it must be true for n plus 1? So we assume the inductive hypothesis that there is some natural number n so that an equals 2n plus 3 is true. We're not assuming this is true for every n. That's what we're trying to prove. We simply assume there is some natural number for which this is true. Then what we need to check is that the desired claim holds true for the next natural number. Notice our claim is not so much that this has to be an n, it's that this index of the sequence appears as what is being multiplied by 2. So if I replace the index with n plus 1, we want to multiply n plus 1 times 2. This line right here exactly matches the claim an equals 2n plus 3, where we simply replace the index with 1 larger. Since the index n appears here being multiplied by 2, when we replace the index with n plus 1, we must also replace the thing that is being multiplied by 2 with n plus 1. So we get to assume that for some natural number, a sub n is 2n plus 3. Now we wish to prove that a sub n plus 1 is 2 times n plus 1 plus 3. But the recursive formula did give us a way to compute an plus 1 if we know the value of an, and we did assume that we do know the value of an, that a sub n is in fact 2n plus 3. So the recursive formula tells us that a sub n plus 1 must be a sub n, which we assumed was 2n plus 3, plus 2. Now, 2n plus 3 plus 2 is simply 2n plus 5, which is actually the same thing as 2n plus 1 plus 3, distributed as follows. And that's exactly what we were trying to prove, that a sub n plus 1 is 2 times n plus 1 plus 3. And we proved that right here. Using the assumption that our desired claim was true for n, and the recursive formula that was given at the beginning of the problem, we were able to show that our desired formula holds true for the next index n plus 1. So whenever we get to assume our claim is true for some n, it must be true for n plus 1. The claim is true for 0. Since it's true for 0, it must be true for 1. Since it's true for 1, it must be true for 2. Since it's true for 2, it must be true for 3, and so forth and so forth. That's the inductive proof. First, show the claim is true for 0, or the first index of interest. Then show whenever it is true for a given index, it must be true for the next one. Those two pieces together inductively give you that it is true for every natural number. Let's take a look at another example. Suppose we have a sequence where c sub 0 is 0, and the sequence is recursively defined so that c sub n plus 1 is c sub n plus n plus 1. Show that for any natural number, c sub n can actually be computed by this right here. We're going to go ahead and use division. Okay, we do know how to compute such things. So we begin our proof with a base case. We check that the claim is true when the index is 0. We were given that c sub 0 is 0, but we want to check our desired claim. Is c sub 0 equal to 0 times 0 plus 1 all divided by 2? Well, indeed, we were given c sub 0 is 0, and that is actually the same thing as 0 times 1 over 2. So the claim does hold for the specific choice of index n equals 0, the first natural number. Now we assume that there is some natural number for which the claim holds. C sub n really is n times n plus 1 over 2. What we want to do is check that the desired formula holds true for index n plus 1. So what we want to show is that c sub n plus 1 is equal to n plus 1 times, in parentheses, n plus 1 over 2. Replace every instance of n with n plus 1. So this subscript becomes n plus 1, this n becomes an n plus 1, and this n becomes an n plus 1. We were, however, given a recursive formula. C sub n plus 1 is definitely equal to c sub n plus the quantity n plus 1. That was given up here as the recursive formula for our sequence. We assumed, however, that c sub n is equal to n times n plus 1 over 2. That was our inductive hypothesis. So c sub n plus 1 must be equal to this quantity plus n plus 1. Well, n times n plus 1 over 2 plus n plus 1. I have a common denominator of 2, so I'll have n times n plus 1 over 2 plus 2 times n plus 1 over 2. Now, if you distribute all of this out, okay, notice what we have is we have n times n plus 1 and 2 times n plus 1. In other words, we have n plus 2 times n plus 1. That's exactly what the claim here predicted. If I replace all of my indices n with n plus 1, we get c sub n plus 1, which is what we have here on the left, an n plus 1, and then an n plus 1 plus 1, or an n plus 2. So what we wanted was that c sub n plus 1 is n plus 1 times n plus 2 over 2, and that's exactly what we got here. So the base case is proved. The claim was true for the specific index of 0. The inductive step is proved. Whenever it happens to be true for a given index n, it must also be true for the next index n plus 1. And those two pieces together complete the proof by induction. A third example can't hurt, so let's take a look. Define a sequence by h sub 1 equals 1, and h sub n is 2 times h sub n minus 1 plus 1. Prove that for all n bigger than or equal to 1, h sub n is given by the formula 2 to the n minus 1. There are a couple of things about this problem that make it a bit different than previous ones we've done. First, we're not trying to show our desired formula is true for all natural numbers, rather for all positive integers, n bigger than or equal to 1. Also, the recursive formula uses slightly different indices than the ones we've seen so far. Here we have an n compared to an n minus 1. In previous examples, we've had an n plus 1 compared to an n. They're pretty much the same thing. This index n is 1 larger than this one, n minus 1. And previous examples, we had h sub n plus 1 compared to h sub n, but still this index was 1 larger than that one. So both of these differences can be addressed. So the base case is no longer n equals 0. If you look at what we're trying to prove, we don't actually want this to be true for n equals 0. The first index that we want this to be true for is n equals 1. That becomes our base case. Okay, the inductive formula will then assume the formula holds for some n bigger than or equal to 1 rather than some natural number, because we are only interested in the n's bigger than or equal to 1. Okay. Then we're going to try to show that the formula holds for all n bigger than or equal to 2. That's going to be our inductive step. Okay? Having assumed that it holds for some n, we're going to try to show it holds for something 1 larger. So for the base case of n equals 1, notice that h sub 1 equals 1 was given. This was just part of our starting information. What we're trying to show is that h sub 1 equals 2 to the first minus 1. That's our formula for the specific choice of n equals 1 for our first relevant index, or our base case. And indeed, 2 to the first minus 1 is in fact 1, which matches the given information. So yes, h sub 1 equals 2 to the first minus 1. That matches our desired claim for the specific index of n equals 1. For the inductive step, we assume that there is some index where the desired claim holds, and then we use our recursive formula. Okay, but our recursive formula, as written, simply tells us h sub n is 2 times hn minus 1 plus 1. But we're not going to assume something about this term here. We still want to assume something about the previous term of the sequence to get the next one. Simply notice that this index n is 1 larger than this index n minus 1. So we can get the following. hn plus 1 is 2 times hn plus 1. That is the same recursive formula we were given. This index is 1 larger than that one, except instead of this being an n minus 1 and this being an n, we've made this term have index n and this term have index 1 larger, which is n plus 1. But now we can use our inductive hypothesis that h sub n can be replaced with 2 to the n minus 1. This distributes as 2 to the n plus 1 minus 2 plus 1. This then collapses as minus 1, and lo and behold, h sub n plus 1 is 2 to the n plus 1 minus 1, which would be exactly our desired claim if all of our indices were replaced with n plus 1. So our inductive step, okay, now says if we know the claim is true for n, it must be true for n plus 1. Our base case was that it was true for the index 1. So therefore, our inductive step says, since it was true for 1, it must be true for 2. Since it was true for 2, it must be true for 3, and so forth and so forth. The inductive proof has been completed. Proof by induction is clearly an interesting technique. It feels very new, and it can do a lot of stuff that we couldn't do before. But we do have to be careful about it. It's actually rather easy to make some errors when constructing inductive proofs. Okay, so the Hungarian mathematician Polya, which I may be horribly mispronouncing, had a very standard classic example of a false proof by induction. Theorem: every horse is the same color. Okay, specifically, we're going to formulate it as follows. Given any n bigger than or equal to 1, if you take n horses, they must all be the same color. I mean, this is clearly false. Horses are not all the same color. But let's take a look at the inductive proof. The base case is n equals 1. If I take a collection of 1 horse, is every horse in that collection the same color? Sure. Whatever color that horse is, it is the color of every horse in the collection because it's the only horse in the collection. So the base case is definitely true. Anytime I have a collection of 1 horse, then every horse in that set is the same. Okay. Now what we do is we make our inductive hypothesis. Anytime you have a set of n horses, They are all the same color. Now this feels wrong, but this is how you would proceed with an inductive proof. You make the inductive hypothesis that the claim is true for some n. If you have a set of n horses, they are all the same color. What we now have to do is show that the claim is true for n plus 1 horses. So suppose you have n plus 1 horses, label them 1 through n plus 1. Now, if I have horses labeled 1 through n plus 1, so I've got horse number 1, and then horse number 2 and 3, all the way up to n plus 1. Previous to that, I had horse n, and previous to that, I had horse n minus 1, etc. If I make all of these horses into a collection, 1 through n, that has n horses in it. Therefore, these are all the same color. Because our inductive hypothesis said, for any set of n horses, all of them are the same color. Well, here is a collection of n horses, so they all have the same color. But I can do the same thing by taking horses 2 through n plus 1. This is still a set of n horses. Okay, it just starts at 2, but I have 1, 2, 3. Notice that horse 2 is the first one, horse 3 is the second one in this specific collection. So this also has n horses. And any set of n horses all has the same color. So these are all the same color. But look, horses 2 through n are in both sets. So if these are all the same color, they're all the same color as these. If these are all the same color, they're all the same color as horses 2 through n. So in fact, horse 1 must be the same color as everything in the middle, and horse n plus 1 must be the same color as everything in the middle. So in fact, they all have the same color. So by assuming that any set of n horses had the same color, we were in fact able to take a set of n plus 1 horses, represent it as two separate collections of n horses, apply our inductive hypothesis to those sets, and conclude that in fact the overall collection of n plus 1 horses all have the same color. But this is definitely false. Okay, this is definitely a false result, so there has to be an error hiding in here. Where is the error? Okay, we were trying to prove it was true for any n bigger than or equal to 1, so our base case is n equals 1. If I have a single horse, it doesn't really matter what color it is. Every horse in that collection has the same color because there's only one horse in it. Okay, then our inductive hypothesis would be we get to assume the claim is true for n. Any set of n horses, all are the same color. You then try to use this hypothesis to derive that the claim is true for n plus 1. So we want to show something is true for any set of n plus 1 horses. So I list them out as horses 1 through n plus 1. 1 through n, that's a set of n horses, so they inductively are all the same color. That's what our inductive hypothesis tells us. But horses 2 through n plus 1 are all the same color because this is also a set of n horses. And if these are all the same color, and if these are all the same color, then overall everything from 1 to n plus 1 was the same color. So everything in this collection must have been the same color, and this was an arbitrary collection of n plus 1 horses. But again, there's got to be a flaw. Where is it? Okay, so think about this for a minute. Where could the flaw in this proof be? It's right here. I drew a picture, and it really looks like horses 2 through n belong to both sets. But they don't actually have to. What if, in fact, n equals 1? Then n plus 1 horses would actually just be 2 horses. So I have horse 1 and horse 2. Can I assume that everything in a set of 1 has the same color? Yes. And indeed, if I start at the beginning and I stop shy of the end, this has n horses in it because n equals 1. And if I then do this set, everything has the same color. But now my picture above is clearly misleading because here, while this goes from 1 to n minus 1, okay, notice that if n is equal to 1, then, sorry, it goes from 1 to n, it goes from 1 to 1, whereas this second collection goes from 2 to n plus 1, 2 to 2, because n was equal to 1, 2 and n plus 1 are both 2. So these are two separate collections of n horses, but they don't overlap. Here I used the fact that these sets overlap to say if these are all the same color and these are all the same color, well then overall they all must be the same. This overlap was crucial. But in the specific case of n equals 1, which was in fact our base case, then n plus 1 only gives me 2 sets, and if I do this little splitting, I don't get any overlap between the 2 sets, and I can't actually conclude that every horse in a set of 2 is the same color. And that's where the proof obviously fails. Okay, if I take a collection of a single horse, then everything in that collection is the same color. But as soon as I ask, well, let's take a collection of 2 horses, that's where intuitively we can tell this is going to go wrong. I can always make a selection of, say, one gray horse and one brown horse, and now I have a collection of 2 horses and they're not the same color. So 2 was going to be where this broke down, and this little diagram explains why. So you do have to be careful when putting together these proofs and when reading through other people's proofs. We're starting to get to where logic gets complicated enough that intuition can fail you, and it can be easy to hoodwink your audience and slip something false past them. If I talk assertively enough, students will believe just about anything I say, but they shouldn't. Okay? Always be on the lookout for false reasoning, like the set from 1 to n and the set from 2 to n plus 1 must overlap. Not necessarily. Okay, so statements that sound very reasonable might actually be false, and you've got to always be alert. Question everything.